These are the two other formulas involving Gibbs free energy that you need to memorize. The first one is change in G is equal to minus RT ln K. K is the equilibrium constant. K can be expressed in terms of multiple of mole per dm cube or in Pascal. So in these questions here, the example that we have is that Kp has a value of 2.5 times 10 to the power of 10 atm. So once you ln it, you will find that it will be a numerical value and is dimensionless. So from that, we can substitute the ln K inside here. And remember that the temperature needs to be in Kelvin. So from there, we can work out the change in G. And in this case, change in G is highly negative and indicates that the reactions could very well move forward since it's thermodynamically feasible. In the next equation, what we have is to relate change in G with the cell potential. Okay, that's a topic that you will learn in electrochemistry. And note that F is the 1 Faraday, which is 96,500 coulomb per mole. That is the data that's available in the data booklet. So you will learn in electrochemistry that if your E value is positive, then the reaction is thermodynamically feasible. And that goes in line with this formula. Since if E is positive, then your change in G will be negative, which also indicates that reaction is thermodynamically feasible. Let us take a look at an example. So in this example that we have, we're looking at the Cu2 plus reacting with zinc. And the first step that we do is to calculate the E cell value or the cell potential value, which happens to be 1.1 volt. So in this case, the 1.1 volt could be substituted inside the E. But what is critical to talk about is the small letter n. N represents the number of moles of electron that has been transferred during this redox reaction. So in this case, zinc has transferred 2 moles of electrons to copper, so that zinc can become Zn2+, while Cu2+ can become copper. Hence, we have to multiply by 2 here. So with that, we are able to obtain a value of negative 212 kilojoules, which indicates that it's again highly negative value, indicating that the reaction is thermodynamically feasible. So what happens if we decide to multiply by 2 to the equation? So instead of 1 mole of Cu2+ reacting with 1 mole of zinc, we now have 2. So in this case, the E cell value is still 1.1. However, for the number of moles of electron transfer, now in this case, there will be 4 moles of electron transfer. And hence, because of that, in this case, your N will now have to be equal to 4. Next one that we look at is that we're going to study reactions that involve boiling. In the case of boiling, boiling point is the same as the condensation point, meaning to say the change in G is 0. So when change in G is 0, we know that the temperature here is the boiling point. So this is the entropy change during boiling, and this is the enthalpy change during boiling. And we can therefore establish a relationship that the boiling point is equal to the enthalpy change divided by the entropy change. And what is interesting is that from the data collected, we realize that when we tabulate the data, we find that most of them has more or less a constant value of plus 88. The reason is because the entropy change of a liquid during boiling or vaporization is more or less about the same for all liquids, regardless of the type of compounds, as the liquid molecules will move as far apart from each other as possible and break away to occupy whatever volume or vessel that is available. That explains why the entropy change of boiling is a constant value of about plus 88 joules per mole per Kelvin. In the case of ethanol and water, there's a deviation from the value, primarily because for the case of ethanol and water molecules, they could form intermolecular H bond. So the intermolecular H bonds will allow ethanol and water to have a significantly lower entropy. So end up during boiling, the change in entropy will be higher than your plus 88 joules per mole per Kelvin. Let's finally take a look at Ellingham diagram. Ellingham diagram plotted chemical reactions with change in G versus temperature. So in this case, we have also manipulated the Gibbs free energy formula such that Y is equal to mx plus C. So you can see that in this case, the gradient of the graph is negative of the entropy, while the y-intercept is actually the enthalpy value. Let's take a look at some example. So the first example we look at is perhaps to look at carbon reacting with oxygen to give carbon monoxide. In this example, we know that the gradient of this reaction is less than 0 because it's negative. Since it is negative, we know that in this reaction, the entropy of this reaction will therefore be more than 0. So the next point that is significant is here. So if we are asked to derive the enthalpy change for this reaction, this will be the value. Okay. Let's take a look at another example. In the other example we're looking at is zinc plus oxygen to give zinc oxide. So in this case, the first thing to note is that it's important to see where the 0 value is for change in G. So the 0 value is here. In order for this chemical reaction to be spontaneous, you want your reaction temperature to actually to be less than this value, which is about 2200 Kelvin. Because when the temperature is less than 2200 Kelvin, we know that the change in G are all in negative values. All right. The second part is that we notice that in this reaction, the gradient, in this case, the gradient is all positive. Because the gradient is positive, the entropy change for this reaction is negative, which is correct because 1 mole of gases as a reactant is being used up in the reaction and leaving behind solid zinc oxide. So a decrease in the number of gas molecules for the reaction will indicate that the entropy change decreases. Finally, we'll take a look at why there's a change in gradient. There's a change in gradient here because at this temperature, which is about 700 Kelvin, that's the temperature when zinc melts. The initial gradient here is less steep, since zinc is solid. But after 700 Kelvin, beyond 700 Kelvin, zinc is now a liquid. When liquid zinc reacts with gaseous oxygen to convert to solid zinc oxide, the decrease in entropy would increase. And therefore, because of that, the gradient will be steeper.